Okay, we're going to continue on lecturing on some organic stuff. So we're going to pick up in that chapter we were talking about. I did a little bit of lecturing with half of you on Monday. The other half I will do today during discussion. So I'm going to pick up from the point where I sort of left off with everybody, or with the discussion lecture. So where we sort of left off, and we talked about last time, we obviously talked about alkanes, and we talked about how to properly name alkanes. Remember, it's all about that longest carbon chain. And we want to find that longest carbon chain, be it the straightest, be it up and over, whatever it may be, but that is essentially what we are looking for. Remember that will match one of our 10 alkane names. We then want to identify the groups that are attached. And a lot of the groups are alkyl groups, which are carbon-containing groups, which means they are also based off of those first 10 alkanes. Then we want to number the chain. And the goal of alkanes in terms of numbering is to give the groups the smallest number. And then we do need to give the location of those groups. Again, we use the dash between number and a letter, comma between two numbers, and we do put the groups in alphabetical order regardless of prefix, and then you kind of build your whole name. We also have cycloalkanes, right, which are ring type structures that are also single bonded. These are our guys that are almost like our geometrical shapes, if you will, in most cases. They are really named also based on how many carbons there are, except that we do add cyclo in front of it. And we add cyclo in front of it. And then basically, if we have only one group attached to it, we do not need to give the number. So we would just obviously give the name of the group along with the cycloalkane name. If we do have two groups, then we do need to give some numbering, and whichever way will give the groups the smaller numbering. We talked about a couple other functional groups as well, which are our alkenes. And those are carbon-carbon double bonds. And our alkynes, which are carbon-carbon triple bonds as our functional group. And these are what are referred to, as we talked about last time, as unsaturated hydrocarbons. They are unsaturated because they do contain at least one double bond or triple bond, which means they do not contain the maximum number of hydrogens that they should have based on how many carbons there are in that case. And they're also based off of really our alkane name here, which is our carbon-carbon single bond. So again, a couple of things that we touched upon. If you have an alkane, which are all single bonded, this is a saturated hydrocarbon, the most hydrogens it should have. Remember that we do sacrifice basically 2 hydrogens every time we put a bond on it. So as we would double bond this guy up, we would lose 2 hydrogens. And as we would add one more bond there to make the triple bond, we would again lose another set of hydrogens, one on each carbon. And again, in terms of names, this again is ethane, A-N-E. This is ethene, E-N-E. And this is ethine, Y-N-E. Any questions on that stuff that we touched upon last time? All right, so let's continue our journey here. We're going to actually focus a little bit on alkenes here and some of the properties of alkenes and some reactions that they undergo. So let us talk about that, which would be here. So when we have alkenes, which are carbon-carbon double bonds, there is something that sort of occurs when we kind of lock everybody into a double bond, and that's pretty much what occurs is when we add the double bond, we lose the rotation around the single bond. So in a single bond, pretty much you could rotate this group around that single bond with no problem. When we get the double bond in there, we lose that ability to rotate around it. So what it creates are isomers. And again, isomers, which I think is something else we talked about last time. Isomers are, again, basically the same formula, but have different sort of connectivity. They create two types of isomers, which are referred to as cis or trans isomers. And cis basically means the same side. And trans basically means opposite sides. And what we're talking about is the location of groups in terms of where they are in relation to the double bond. So if we have a double bond between two carbons and we have a group like this, these two groups, which are just A in this case, they're on the same side of the double bond, and that would be what is referred to as the cis isomer. We could also have the double bond where perhaps the groups are on opposite sides of the double bond. Guess I'll use a different letter. I'll use D. And B here, I think. So our A's are on opposite sides, and that would be our trans isomer. So the double bond basically gives rise to these type of isomers where we basically have groups either on the same side or opposite sides of the double bond. And once again, that one that got cut off there on the screen, we have it basically on opposite sides there of the double bond. So how do you know if you could have a cis or trans isomer? And there's a couple of things you have to make sure of when you look at the double bond. It should always be by the double bond. And when we look at the double bond, a couple of important things that you want to make sure of in order for it to even be possible for a cis or trans isomer, and that is each carbon in the double bond needs to have different groups. So each carbon needs to have different groups attached to it. And by the way, when we're talking about groups in this sort of aspect, hydrogen can be considered sort of a group in this aspect when we're thinking about cis or trans. So again, you know, if you got something like A and maybe D again here. So again, we have different groups attached. The other thing that you need is, in addition for each carbon to have different groups attached directly to it, you need to also have obviously a group that is in common on opposite carbons. So you need some type of group that's in common on opposite carbons in order for that to occur. And in this case, obviously, it's the A's that are the same and opposite carbons. So if you end up with something, say, like this, this right here, when we look at it, this would be the double bond we would want to focus on. When we look at the carbon on the left, it has a hydrogen attached, but it has another hydrogen attached to the same carbon. That means this cannot have cis or trans. So that is what we mean when you cannot have the same group attached to the same carbon. It eliminates the possibility of cis or trans basically occurring. So if we look at this guy down here, this is the double bond that we would want to focus in on. And here we have a chlorine and a hydrogen. Those are different groups. This is a chlorine and a hydrogen, which are also different groups. And again, in this case, the chlorine is shared between the two carbons. And that chlorine is on the same side of the double bond, and that would be our cis. So sometimes the word cis is added to the name to indicate that the groups are on the same side of the double bond. If we drew it like this, once again, looking at the double bond here, we have a group here and a group here that are different. On this carbon, these two groups are different, so that is good. And once again, in this case, though, we do have our groups on opposite sides of the double bond, and that would make it trans. In terms of naming, we would name it like normal. The longest continuous carbon chain in this particular example is right there, which is 2. Also there, which is 2. and that is where the ethene parts comes from because it has a double bond. And the 1,2 dichloryl ethene is because, again, those chlorines are in carbon number 1 and number 2, since there's only 2 carbons there. And again, we would add our cis or trans to the beginning of it. Questions on that there? So cis and trans isomers have different physical and chemical properties. And again, if you kind of use your fingers as a double bond, thumbs up, thumbs opposite, or cis and trans. In a cis isomer, again, the alkyl groups are attached to the same side of the double bond and the hydrogens are on the other side. So in this case, these would be some methane groups or methyl groups, and they're on the same side. And in this case, we have methyl groups on opposite sides here. By the way, when we go to name this longest carbon chain is 1, 2, 3, and 4 there. So that is where butene comes from, as it has a double bond in it based off of butane. So naming our cis or trans, again, we really just name the compound like normal, and we add either cis or trans to it. If you were asked to draw a cis or trans sort of compound, I would recommend maybe drawing 2 structures, one just like a normal structure, and then afterwards kind of turn it into either the cis or the trans that you're trying to draw. So what I mean in this case is, for example, if we were going to draw this guy, we would go backwards. And when we see ethene, it tells us a couple of things. Ethene is based off of ethane, which means it should have 2 carbons. Ethene is a double bond, right? ENE, so it would be actually a double bond between the 2 carbons. And just like normal, we would sort of get rid of that. At carbon 1 and 2, there's a bromine group. And since there's only 2 carbons here, each of these guys would have a bromine attached. And the rest here, like normal, would be hydrogens, right? Now, the way I just drew it actually is the cis or trans one, actually. I ended up actually drawing the cis, right? The bromines are on the same side. So if I needed to redraw in a trans form, I would just start with the carbons. And again, move my bromines to the opposite location. And obviously put my hydrogens in there. And now I have the trans one. So sometimes it's easier if you're drawing either cis or trans just to draw it kind of like normal, and then go back, isolate the double bond, and then just kind of move the groups where they need to be moved, rather than trying to draw it right out of the box as either cis or trans. Sometimes it's a lot easier to kind of go backwards and do that. Any questions on that there? All right, so we'll do just the cis and trans part of these. So for each of these, determine if they are cis or trans, and then we'll go through the naming together. Actually, if you want to give it a try naming. Again, we do name these things like normal. We want to use ENE because there's a double bond. We also want to give the location of the double bond if it is more than one place it could be at. So okay, let's take a look and see. First off, cis or trans. First one is cis. If we isolate the double bond here, we got a carbon over here that has 2 different groups attached on both carbons, so that's good. It shares a chlorine on both carbons. It also shares a methyl group right on both carbons, and either one is on the same carbon, on the same side of the double bond, and that would be a cis in this case. The second one should be a trans. Again, we got this different groups on each of the carbons, but we do have, for example, if we look at the bromine, have the same group on opposite sides of the double bond, so that would be trans. And the last one here is also going to be trans as well. Again, we have a methyl group on opposite sides, which would be trans. First off, any question on cis or trans? Okay. So in terms of naming, if we want to go name these guys, again, they are alkenes. So we're going to have a little bit different naming. Clear this stuff out here. We want to look for the longest continuous carbon chain. And sometimes when people go to name these guys, they focus a little bit too much on the carbon-carbon double bond. Longest continuous carbon chain is here. That is a 1, 2, 3, and 4. That entire thing is the longest continuous carbon chain, not just the 2 in the middle that look like a double bond. So that's really important not to miss it. That is going to be 4 carbons, which is based off of butane. It would then become butene because of the double bond. In this case, we would number the carbon chain to give the double bond the smallest number. And if you look at it, it really doesn't matter which way you go in this particular case. You could go 1, 2, 3, and 4. No matter what, that double bond is going to end up at carbon number 2, no matter which way you go. So we would incorporate that into our naming, which is a little bit different than what we do with alkanes. We have to give the location of the double bond. It also takes the priority in terms of numbering. So that would be 2 butene. That would mean that we do have a chlorine group at carbon 2 and a chlorine group at carbon 3, and that's 2 chlorine groups in the same compound. So that's going to be a dichloryl. And the numbering here would be, as I run out of room, I'll go underneath it, 2,3 dash 2,3 dash dichloryl 2-butene would be the name here. Any questions on that one? Now, if we look at the guy underneath it or in the middle, we're going to kind of end up similar here. Once again, that is 1 carbon, 2 carbons, 3 carbons, and 4 carbons. And again, in this case, the longest carbon chain does need to contain the double bond. And that would make this also butene. And we're going to get really the same numbering scheme that we had a minute ago there. So that's going to be 2-butene. And in this case, we actually have 2 bromines as the groups. Although the methyls are considered a group as we're looking for cis and trans, in this case, the methyls are actually part of the longest carbon chain. So they're technically really not a group. It's actually just the bromines here that are the group. And that would give us dibromal. And then our numbers, which would also be 2, 3 here. Any questions on that name there? Lastly, we have this guy, which longest carbon chain still going to be R4, which is butene. And double bond still going to be our carbon number 2, which would be 2-butene. And when you look at it like that, there is actually no other groups attached, right? So that is your entire molecule. I'll put like a little dash in between. So that'd be trans to butene, in this case, ENE at the end of it. Any questions on any of those there? Cis or trans isomers. So again, you need to make sure those couple of things that you have different groups on the same carbon, but you do obviously have a group that's in common on different carbons in order for cis or trans to occur. Any questions on that there? Okay. All right, so let's actually talk about some reactions that alkenes undergo. And alkenes undergo what are referred to as addition reactions. And addition reactions are pretty much what it sounds like. We're going to add something in. So all the alkenes that go through addition reactions, pretty much everything happens right there at the double bond. You could care less about everything else. Everything else will stay the same. The absolutely only thing that will happen is going to happen here at the functional group, which is where our double bond is. So all the action here in terms of the addition is going to happen right at that point. So what we will add to it could be something that is 2 of the same thing. Could be something that is maybe two different things that are going to be added to it. It really doesn't matter. But what will always happen in these reactions is this. Pretty much, if I wanted to put something onto this carbon or this carbon, could I just add something to it the way it is? I could not, because with that double bond, right, it's now got 4 bonds each of those carbons. So if you just try to stick something on each of those carbons, you're now going to have 5 bonds, which is, again, too many bonds per carbon. So what always happens in an addition reaction is pretty much this. You go to the double bond. You need to make room for what's coming in. So the double bond becomes a single bond. So always the double bond becomes a single bond. And what that is going to do is open up basically a space for whatever's coming in. So the nice thing about that is, frankly, you have the picture drawn for you right there. You just need to draw it exactly like that, but make the double bond into a single bond. Don't overthink it. Don't overcomplicate it. Just copy what's there. Turn that double bond into a single bond. And now if we look at each of the carbons and what we just drew, they're actually short a bond, right? They only have 3. That's good, because now we want to take whatever we're going to add, and we want to take each one of these will end up at a carbon. So each one of these will end up at a carbon. So if I did that, I now have room to add those in. And that is all she wrote on an addition reaction. So in an addition reaction, we basically make room for what's coming in by turning the double bond into a single bond. Then we put one guy on one carbon that was in the double bond, and the other one coming in goes on the other carbon. They never get added to the same carbon. So they always go to opposite carbons in the double bond in that sense. Any questions on that there? Okay, so there are a couple of different types of addition reactions that we see with alkanes. Some are what are sometimes referred to as symmetrical additions, and some are referred to as unsymmetrical additions. So let's talk a little bit about first sort of symmetrical additions. That basically means we're going to add something that's the same, like H2, you're going to add 2 hydrogens. Cl2, you're going to add 2 Cls. Br2, you're going to add 2 bromines. So the nice thing about these type of reactions is you really can't screw it up, because hopefully you're adding the same thing to each carbon. So you don't have to worry about where goes where or which one goes which. So usually some type of catalyst is used. And you'll sometimes see these catalysts like platinum, nickel, palladium sort of written on top of the arrow. They really have no effect on what's happening, other than it will just kind of speed up the reaction and make it sort of occur a lot quicker. So for example, if I had something that looked like this, and I wanted to add, maybe we'll do some Cl2, which is this basically. Probably have a little catalyst to help me. So although there is a lot of carbons going on in this thing that I drew, the only place it changes is the double bond. So that is the only place that basically will change. Once again, you should not do any fun stuff like make weird things happen, like rings and stuff like that, just because it seems more chemistry-like. Pretty much that is what's going to happen. So what that means is you pretty much have 95% of your picture done for you. You just need to copy exactly what is there. The only thing you need to do is turn the double bond into a single bond. That's pretty much all you need to do. So that is what I'm going to do. I'm just going to copy it pretty much starting here and going all the way across. I'm just going to draw it here because I don't want to go off the screen there. So I'm going to go down here and we'll do this. We'll do this exactly the same. Nothing's changing. Now I'm getting to my double bond. I'm just going to make it a single bond at this point. And I feel like I had too many hydrogens there to begin with. Bad instructor. Try that again. Get rid of that. There we go. That's better. Let me get rid of that one too. There we go. All right. Now I have the right number of bonds. Too many bonds before. Not good. All right, so we're going to continue to copy now the correct one here. Double bond becomes a single bond, and now we are good to go, right? So at the end, it now needs something there, right? Because it only got 3 bonds, and the guy to the left, now that I got rid of that extra hydrogen, only has 3 bonds. So that is where we're going to put our chlorines. And in this case, because it's really the same element that you're adding, you can't mess it up. You're just going to put a chlorine there and a chlorine there, and you are done. Yeah. So it's really important not to overcomplicate it and do all kinds of weird things that you think, well, maybe, that's what should happen. Any questions on that there? You have that. Okay, so let's put the page. So let's take a look at we'll look at another one here. Why don't you try one? So why don't you do this guy here. Try not to make too many bonds here this time. There you go. So why don't you do this plus some bromine? Why don't you do this guy plus some hydrogen? All right. So don't overthink it. Do what I just said and see what you come up with here. Functional group there, and also here is the thing where everything's going to happen. Once again, everything remains the same, except that in this case, we know we need to make room for what's coming in. So the only thing that's going to change is we're going to turn that double bond into a single bond. So for me, I'm just going to start copying exactly what's there. I'll go a little bit below there so I don't run out of room, hopefully. We got that. We got this. And now I'm going to turn, again, my double into a single. Everything else that's attached is still the same. Again, nothing weird happens. Things don't form rings or anything like that. Now we can see clearly we got 2 spaces, one for each of the bromines that could go on there. So we would put a Br there and a Br there. Any questions on that one? Again, symmetrical addition, you're adding the same guy. Can't really mess it up, hopefully, because you're putting the same element there. Over here, even though it's a cycloalkene, it still works the same way, which means all I'm going to do is redraw exactly the same structure, except I'm going to eliminate the double bond, which actually will open up a room for what we're going to put in there. So pretty much this one's not too bad. You're just going to recopy it exactly like that. And honestly, that's actually the right answer because the hydrogen's assumed to be there. But since we are adding the hydrogens, we will actually draw them in. And basically, we're going to put a hydrogen on that spot and a hydrogen on that spot, which technically you don't really need to do in a line structure like that because it's technically there. By the way, when you do this, this is what is known as a hydrogenation reaction because you are adding hydrogen. That's how they partially hydrogenate your oils, yes, and get rid of the double bonds, and it makes it things like margarine and those type of things. So when it says partially hydrogenated, that's basically what it means. They basically got rid of a lot of double bonds by adding hydrogen to it and made them from double bonds to single bonds. What that does is we'll talk about when we talk about fatty acids is it actually makes things a little bit harder in terms of fats. Things with lots of double bonds are more like oils and stuff like that. And things that have less double bonds, more single bonds, are more like margarine and butter and harder sort of fats like that. Question on this type of reaction here. Now, this is a symmetrical addition, and we could have an unsymmetrical addition, which means we're basically adding 2 different things. So instead of like 2 hydrogens or 2 bromines or 2 chlorines, we could have what is sometimes referred to as an unsymmetrical addition. And that basically just means in a lot of cases, we will add something like water. And we think of water a lot of times when we're doing this as like H and OH is sort of how it gets added. You could add something like HCl, HBr, hydrogen and something else being added basically to the double bond. It really does work the same way. So there's not much of a difference. We will take, say, something like this. Okay, we'll do this guy first, I think. So if we were to add water, and again, that is sometimes in these chapters sort of displayed as H and OH as what's being added. Same thing's going to happen. It's all going to happen right here at our double bond. And just like the other one, we don't have room for it. So we need to make it into a single bond. So what we would do again is just draw it exactly the same. And we would then make everybody a single bond. Now each of those carbons have a spot for either the hydrogen or the OH to be added. And in this case, we could add the OH here, and we could add the H here. This went from an alkene to an alcohol, right? This is how we make alcohols. Basically, hydration reaction is what this is sometimes referred to. Hydration means that we are adding water. This is what is known as ethene. This is what is known as ethanol, OL. Basically 2 carbons with the OH group, which is the alcohol group, and that is ethanol. Now, there could be a situation where it doesn't really matter where you put the OH or the H. In this particular case, it doesn't matter, because if I put the OH on the where I put it, it would be ethanol. If I put the OH on the other side, it would still be ethanol. It's the same guy, just basically turned. There could be a situation where it would matter perhaps where you would put it. Let me see what I could do here. We'll go with do this maybe. Out of here. All right, so let's say I put some water on this guy here. Now, in this particular case, when we look at this, the same thing is going to happen. We're going to basically make that double bond into a single bond. So everything else, again, will be the same. So we're going to turn that into a single bond here. And we got this going on. And one option would be to put the OH group here and the H here. That would be one option. The other option would be the opposite. So if we did the opposite here, and again, just started with the exact same guy, just with a single bond. And do it this way. There you go. H and OH. Now, when we look at this, we still made alcohols, but we actually made some different alcohols in this particular case. We have longest carbon chain is 3, right? And on this guy, straight across there. So 3 with the OH group right about there, that is propane, and OL becomes propanol. OL. OH group gets the priority in terms of numbering for the smallest number. So we would probably number this way, and this would be known as 2-propanol. And there also is a methyl group here, which would be 2-methyl 2-propanol. So obviously we'll go over naming all this, but that would be 2-methyl 2-propanol. If we want to name this guy here, longest carbon chain is still propane, which is propanol. The OH group, though, now is at carbon number 1 here. So that would be 1-propanol. And my methyl group is at carbon 1 and 2. So that would be 2-methyl 1-propanol. So in this case, it actually makes a difference depending on where you put the H and the OH. And I just illustrated the names here to show you that you actually do get 2 different alcohols. and two different products as a result of this. This is sometimes what is referred to as having a major product and a minor product. And usually when you want in chemistry, you want to usually draw the major product. And there is a rule that's sometimes referred to as Markovnikov's rule. I won't spell it, but it's with an M. So it's Markovnikov's rule. And basically what his rule says is whenever you're doing an addition reaction and you're adding hydrogen and something else, if there is an option, the hydrogen should always end up. So the hydrogen should always end up at the carbon that had the most hydrogens to begin with. And what we're talking about is coming back to our original double bond and looking at the original carbons in our double bond and how many hydrogens each one has attached directly to it. The one on the right has how many hydrogens directly attached to it? On the original guy, it is 2 hydrogens, yeah. The guy on the left has how many hydrogens attached to it? 0 directly attached to it, right? Because the other ones are carbons that are attached to it. So in this case, really the hydrogen should end up right there on the one that had the most hydrogens to begin with, which means what I've just arrowed would be the major product and really the one that you should draw. So that is the rule when you're doing sort of unsymmetrical situations. If there is options where it does make a difference, there's different numbers of hydrogens basically on the carbon that's in the double bond. The one that has the most hydrogen should get the hydrogen and the other guy should go to the other carbon that's in there. Any questions on that there? Let's take a look here. So as I mentioned earlier, this is what is referred to as a hydration reaction, which is symmetrical. Again, usually some type of catalyst is used. And again, in this case, we're just going to break the bond and add the hydrogens in. And that is, again, what is sometimes referred to as a hydrogenation reaction. The catalysts really have no effect, again, on the product. So they're just there, I won't say for decoration, but really to speed up the reaction. All right, so why don't you do that? What is the product of 1-butene? And by the way, butene, 1-butene will look something like this. All right, so why don't you draw the product of this? Hydrogen, still going. Of the hydrogenation, which means we're going to add H2. All right, so let's take a look. So remember that you pretty much have your answer kind of staring at you in the face. So don't overlook that when you have a problem like this. Again, you just want to really focus in on the functional group here. And we know that this is going to need to make room. So we just want to turn it into a single bond. And you should just literally copy it just like that without thinking too much, because you might talk yourself out of the right answer. Yeah, so we will end up with the exact same thing as what we started with. And in this particular case, it is a symmetrical addition. So we're just adding hydrogen. And now that we got rid of the double bond, we now have room for it. And we're going to put a hydrogen there and a hydrogen there. Yeah. Now we are done. We went from an alkene, right? And through a hydrogenation reaction, we ended up with an alkane. Yeah. So that is how you can make an alkane from an alkene. Basically add hydrogen, gets rid of the double bonds, basically. Yeah. Any questions on that there? All right, so as I mentioned before, that's what hydrogenation of oils are. Removing those double bonds really moves fatty acids from more of an oil, liquid sort of state to a more solid type of state. And that really has to do with, this is a fatty acid here, and it has to do with the long carbon chain that there is. And what happens when you get double bonds together and a bunch of double bonds together is when you get a bunch of these molecules together, they really can't sit nicely with each other. So they kind of like go all over the place and they don't really pack together really tightly. The result of that is it ends up being more of an oil or a liquid type of state. When you have pretty much all single bonds, that back end will fit really nicely as they start to stack on each other. And that's where you get sort of harder fats, like what you see in steaks and butter and, those type of things, is those type of fats that will occur. We'll talk more about that when we get to fatty acids. All right, so why don't you do these two here, but actually let's mix it up. Let's do that one, and then the same guy, let's add HBr as well. And for this one, let's add water as well. All right, so do all four of those. Okay, let's take a look. So once again, everything going to happen right here at our double bond. And we're going to make it into a single bond to make room for it. So I'll do the first one, which is the H2 first. We will go CH3, C. I'm going to draw the hydrogens just so we could kind of see it there. Again, I'm going to turn the double bond into a single bond. And again, I'll draw the hydrogen on this guy as well. And then the rest there will be the same. Now that I did that, again, you can see that those carbons have room for the hydrogens. And since this is symmetrical, we just pretty much just need to put a hydrogen in each of those spots, right? If you did condensed formula, you just make it CH2, CH2 basically here. Question on that one. Looking at the bottom one, we're going to do really the same thing. So I'm just going to start with the same structure by making my double bond into a single bond in this case. Now, this is an unsymmetrical addition, and remember that we only really have to worry about the hydrogen if the carbon-carbon double bond has different numbers of hydrogen. So in this case, do they have different numbers of hydrogen? They both have one, right? So it really doesn't matter in this case. You'll end up with the same thing. So you can really put it whichever side you want to put it. You could do the H there and the Br there, or you could flip it around the other way. And because they both have the same number of hydrogens, it will be the same result. Question on that. And again, if we named it going this way here, we would call it 1, 2, 3, 4. And that would be butane, and that would be 2-bromobutane, right? If we name that, that would be 2-bromobutane. If I drew it the other way around, which my CH3 would be here, my carbon would be here, my bromine would be here, my hydrogen would be here, my carbon would be here, my hydrogen would be there, hydrogen, and that also would now be called 2-bromobutane. So it's the same. And that's because that carbon-carbon double bond had the same number of hydrogens. So it doesn't really matter. You're good to go either way on that thing. You just have to worry about it if it doesn't have the same number of hydrogens. All right. Here we're going to do the hydrogenation reaction first of this guy. And once again, this is the only part that changes. And by the way, it does not open up. Yeah, so it stays closed. Yeah, so people always want to like open it up and draw it straight or something like that. So it stays the same. So we're just going to draw it exactly the same. Obviously, we're going to eliminate the double bond. And once again, in this case, we're just adding hydrogen. So we would, again, you really don't necessarily have to write the hydrogens in this case, but just to show you, that is where the hydrogens would end up in that particular case. Yeah. On this last one, okay. Yeah. About for the product that we drew, or
well, on either one double bond, we did the H's with the line connected.
Yeah, so it would be if you're asking what it would look like, it would be like CH2 to CH2 to CH, right? And then you got your double bond, and then to another CH, right? And then this would come down to a CH2, and then over that way.
Taking out that double bond and putting a 2 and 2.
Yeah, you could do that as well. Yeah, absolutely. Yeah. So the end result, you could just put CH2 all the way around there. Yeah. Now let's take a look at the water here. In this case, we would start with the same thing here. Oh, there it goes. Ish, strong, British. Does it matter in this case where I put the H or the OH? It doesn't. It's the same thing. They both have the same number of hydrogens, right? They both have one to begin with, which means, again, you could do whatever you like. You could put the OH there. And again, you don't necessarily have to draw the H, but I'll put it there, which would be there. Or you could obviously flip it around. That would then be called not cyclopentane, but it would be cyclopentanol, OL. Yeah. So as an OH group, this would be cyclopentanol, OL. Question on any of those reactions there? All right, so the hydration reaction is typically when we do add water, and as I mentioned before, there is what is referred to as the Markov, definitely not spelled right, rule, which is, again, that hydrogen, when there is an option and that double bond starting with different numbers of hydrogen should always end up at the carbon that had the most hydrogens to begin with. The other thing that you're adding will end up at the other carbon. So why don't you try that the one there and see what you come up with. Okay, so once again, we're going to focus in really just there, and I'm going to redraw it again, removing the double bond, making it a single bond. And I'm going to also draw out all the hydrogens just so we could kind of visualize everything. I'm going to go underneath it to do so. So I'm just going to draw that CH3, then our CH2, then our CH. Now my double bond will become, again, a single bond at this point. And I do have two hydrogens there. So in this case, we are adding water, which is basically H and OH. This is a acid catalyst is what that is a reference to. Not really going to do much in terms of our purposes here, but you'll just sometimes see maybe that or H2SO4 written up on top of the arrow as a catalyst. Doesn't matter where the hydrogen ends up here. That is both answers, yes. So one of those should be right. And the one that's right is it does matter here, right? When we look at where the double bond was originally, the carbons have different numbers of hydrogens attached, right? The one on the right has 2. The one on the left has 1, which means the hydrogen should end up on which carbon? The one with the most, which would be the one on the right here. So we should put the hydrogen here as it has the most hydrogens to begin with. And then our other guy gets our OH. And now we have our alcohol, which, by the way, would be 1, 2, 3, 4 carbons, which would be butanol. And the OH group is at carbon number 2, which would be 2-butanol, 2 for where the OH group is located, basically. Yes. Question on that. So again, in a situation, and the way you could really help yourself visualize it is to do probably what I just did, just redraw without the double bond and then draw out all the hydrogens, and then you could clearly see, hopefully, there are different numbers of hydrogens, and then I'll help you decide where you should put it. Question on that there. Yeah. It wouldn't necessarily be wrong. I'll say, well, I won't say it necessarily be wrong, but this is what is sometimes referred to as the major product, which is really most of the time what you would get as a result of this reaction. And that's usually what you want to draw. Now, if we did the opposite, which is what you're asking, basically put the OH on the other side and the H on that side, we would end up with something that looks like this. And again, here the H, and I'll circle it, would go there, right? And the OH would go there in this case. And again, it's not necessarily that it is super wrong or anything like that, but this is what is referred to as the minor product. And The reason they're different is because they're actually different types of alcohols. So if we want to go name this guy, we would still have 4 carbons, which would be based off of butane, and this would be butanol. But the OH group here would be located at carbon number 1. So this is 1-butanol. And the bottom guy would technically be 2-butanol, which are 2 different alcohols. And as a result of this reaction, following the rule, this is typically what you should get. Now, if we look back at sort of what we did earlier on the previous one here, for example, when we did this guy and we started out with the same number of hydrogens on each of those carbons in the double bond, when we put this hydrogen here and this bromine here, we ended up with something known as 2-bromol butene. When we switched it around and did it this way, if you were going to name this, this also would still be 2-bromol butene. It is the exact same molecule in both cases. And that's what occurs when there's the same number of hydrogens to begin with. It doesn't really matter where you put it. You'll always end up with the exact same compound. It's just turned. And that's why it doesn't make a difference. But when you do have an option where there is a difference, you actually will end up with 2 different sort of organic compounds, and they have different properties and they could have different sort of characteristics as well. So in most cases, you always want to kind of shoot following for that rule, which is the major product. And again, technically the other one is sometimes referred to as the minor product, which means, so for example, what it basically means is, like, for example, 93% of the time, that's pretty much what you get. And maybe 7% of the time you get the other guy that will come out. So usually what you're looking for is a majority of what you get in most of the cases. Other questions? All right, so to finish up this chapter, we're going to talk about aromatic compounds. Aromatic compounds are based off of what is referred to as the benzene ring. And it needs to have a benzene ring. And a benzene ring is this guy down here. It is a 6-carbon ring that has 3 double bonds in it. So it's either that, you could draw a resonance structure where it looks something like this, double bonds over here. And a lot of times in our book, they will draw a benzene ring with like a circle in the middle. And that's because those double bond electrons are basically moving around. So at any given point in time, it could be like the guy on the left, could be the guy on the right. So sometimes we'll just draw like a circle in the middle. This should definitely not be confused with 2 other things that sometimes it is confused with. And that is this with no double bonds. That with no double bonds is cyclohexane, which is different than benzene. Yeah, so those are different things. And even a 6-member ring that has just 1 double bond is still not benzene. That is cyclohexene. So those are different things. So this is cyclohexene, E-N-E. This is cyclohexane. And all 3 of these guys down here are benzene. So in order to be benzene, you got to have those 3 double bonds in there. So sometimes people get confused, like it looks like the same shape. So it's clearly going to be the same thing, but those double bonds are important. Any questions on that? I would say most of the time when somebody draws a benzene ring, it's line structure. Most of the time is how most people will draw it, is sort of that line structure. Good. Super zoom. All right, good zoom. So benzene, again, like I said, looks like that. And that means that there really is a hydrogen, as you can see in this picture, at each of those carbons. So it does have 1 hydrogen. And I would say probably a majority of the time in your book, you'll probably see it drawn more like that with the circle in the middle. You could really draw it either way you like. Now, there are some historical sort of compounds that are sort of benzene based that have groups attached. This one is a historical sort of compound and name. This is what is, bless you, which is known as, bless you, which is known as toluene. So this is known as toluene. You could also call it kind of like by its other name, which is, this is a benzene ring, right? And attached to it is what group? That is a methyl. So this is sometimes referred to as methylbenzene. but a lot of times still people still call it toluene. Again, it's a pretty historical name that's used a lot. This is what is known as aniline. And this is, we'll talk about later, sometimes referred to as an amino group. And sometimes this is what is referred to as aminobenzene. But a lot of people will still call it aniline. This is sort of the alcohol version of benzene. That's an OH group, which is an alcohol group. And that's what's known as phenol. And those three names do still pop up a good amount, and maybe in your book as well, it'll still maybe pop up. So you should sort of be familiar with those guys. Now, everybody else as our groups, we do just basically name it like normal. So we will, if it's just one group attached, you just give the group name and put benzene at the end. So that is chlorobenzene. You do not need to give the number because in this case, wherever that group is located, it's assumed to be carbon number 1. But if you do have multiple groups attached, you do need to give some numbers. So this is 1 and 2 dichlorobenzene. This is 1 and 3, which is 1,3-dichlorobenzene. And this is 1 and 4 dichlorobenzene. This also has other relationships that are sometimes used. The 1 and 2 relationship on a benzene ring is also sometimes referred to as the ortho relationship, and sometimes just abbreviated with an O instead of the numbers. So they may just say O dichlorobenzene, which means you got guys at 1 and 2 positioning. The 1,3 positioning is what is sometimes referred to as meta on the benzene ring, or M. And again, sometimes people will just say M dichlorobenzene, and the M means you basically have it at position 1 and 2. And the 1,4 positioning on the benzene ring is the para positioning, and sometimes just referred to as P. And if you see like P dichlorobenzene, it means you got a group at 1 and 4 on the ring. The nice thing about the sort of benzene ring is it has those 3 double bonds, which means you could go clockwise or counterclockwise. You will always be going through a double bond. So it doesn't really matter sort of which way you number, whichever way will give the smallest for the groups that are attached, you will be okay. Any questions on that there? So if we look at some of these names here and how we get there, this entire thing with the NH2 group is aniline, as we saw on the previous page. And because that's sort of part of it, that would be carbon 1. Coming here is carbon 2 and carbon 3, and that would be 3-bromol aniline. This part here is the phenol part, which is that alcohol, which would make this group number 1. This would be group 2, group 3, and group 4. We wouldn't go the other way because then we would end up with 2, 3, 4, 5, and 6. So much larger numbers if we went obviously clockwise versus counterclockwise. And that is where we get our 4-bromol 2-chlorophenol. And obviously toluene is this part right there. And again, that would take the priority and have carbon number 1. And in this case, you can kind of go either way, and you'll have your 2,6-dibromol 4-chloral toluene is that part, the back part. So if you have one of those historical sort of guys with benzene on it, whatever group is on there, like the methyl group, the OH group, that will always be carbon number 1, and then you would number everybody else accordingly, whichever way will give them everybody else the smaller number. Any questions on that there? All right, so if we took a look at this here, the name of the first guy should be that is a chlorine group or a chloral group. That is a benzene ring, and that is chlorobenzene. Yes. This guy here would be, yeah, so this is a benzene ring. They decided not to use toluene here, right? So this is going to be carbon 1, carbon 2, carbon 3. we went the other way, this would be 1, 2, 3, 4, and 5, right? Much bigger number if you went the other way. So again, we always want the smaller number. So that is a 1, 3 dimethylbenzene. That is also what positioning? That's the 1, 3 positioning. That is the meta positioning. So that's meta dimethylbenzene as well. Yeah. Question on the benzene ring. Yeah. Yeah. Oh, the position. Yeah. Yeah. Did you have a question or you just want to look at it? Yeah, so you need to know, you do need to know that ortho is the 1, 2 positioning on a benzene ring where the groups are attached. Meta is the 1, 3 positioning, and para is the 1, 4 positioning. It does happens to pop up occasionally. It's still with the benzene ring. And it's specific for benzene rings and the groups that are attached to the benzene ring. Other questions? All right, we will lay it up there.